I am set up. Now, can you see full screen my slides? Can you see?
Everything looks fine.
Yes.
But the pointer disappeared. I have only a small hand here, so then I still try to annotate again. Spotlight. That's perfect. I have it, but I have this stupid bar, and it seems to be when I attempt to close it, the pointer disappeared. Do you see the bar with the menu? Not.
I see this red spot. It's working.
The red spot, but not the zoom bar with the icons.
Mm-hmm.
I can move it down. That's good. Then it will not disturb me. Very good. Okay. Now I think I'm clicking here. Up. Okay, I understood from our organizers of the seminar that I have about 1 hour. I'm not then rushing. And not to rush at all, even to be didactic and slow and explain as simple as possible. I selected for the seminar only 2 topics in the broad field of fluctuations in general, but I first, of course, I was invited and narrow my seminar to fluctuations at the CERN SPS. But even from this already narrower topic, I selected only 2 subjects, multiplicity fluctuations. We will go from PP to E plus E minus and AA collisions. This will be the first half an hour, and the second half an hour critical point search. And here again, instead of giving a review of how critical point was searched at the SPS, I will just address one subject search using so-called intermittency analysis. I selected these 2 subjects because I like them, first of all. Second, because probably you are not very familiar with them. It's somewhat outside, I believe, typical analysis subjects at RHIC. So that's maybe because of this will be these 2 subjects may be new for you, at least some of you, and interesting. Now, what is special at CERN SPS? Selected 2 plots. The left shows the scaled variance of charge particle multiplicity as a function of mean multiplicity. We are here increasing, we can here increase multiplicity by different means. First of all, collision energy. Let's focus on this. So we stay with PP collisions, and then you see the small dots here. These are data, PP data, recorded at SPS, but also at PS and other machines. And they go straight, right? Straight up. Scaled variance in increasing. Whereas the statistical models, simplifying a bit, I will go during the first hour through details of this plot actually. They predict independence of the scaled variance with charge particle multiplicity, for instance, increased by increasing the volume of the system. So, and you see that as SPS energies, approximate ranges of accelerator are indicated here. In the SPS energies, the two dependencies cross each other. First of all, qualitatively different, and they cross each other at SPS energy. So that's the first half an hour. Second, the popular phase diagram of strongly interacting matter. I don't have to introduce this to you. Biochemical potential, temperature, hypothetical first order phase transition line, which ends in the critical point. We call it now DCP, deconfinement critical point, to distinguish from nuclear critical point, which sits somewhere here down. This is hypothetical. We are searching for it. You at RHIC, we are at SPS, and I will report on this search in detail, but limiting myself to the intermittency method to search for the critical point. As you see here, I indicated in the, not I, but that's a plot from the big activity of CERN summarizing physics beyond collider. Collider is indicated in shaded areas, gray areas, regions covered by CERN machines, first of all SPS, and there's a good chance that we may have a find critical point at CERN SPS energies. Then we have LHC fixed target program, which is just developing, and this connected gray region indicates potential reach of this program in T-nu-B, and the LHC as a collider, you know perfectly that that's very close to zero, very nu-B and high temperatures. RHIC is somewhere here with your best program, actually covering pretty large area over here, right? The two programs are covered by the RHIC best programs, different versions with fixed target collider. Good. Let's go to the first part, the multiplicity fluctuations from PP to E plus E minus to AA. I will go back in the past, like beginning of 70s, when we studied, not we, I was still not really active, but our colleagues studied very extensively PP collisions, different machines, different energies. This is a photo of bubble chamber at 24 GeV. This was PS, not SPS at CERN. And you see multiplicity, of course, is slow. You can count all these tracks. If you have detector in magnetic field, you can say what is positively and what is negatively charged hadron. So beauty of this experiment is that you have a full acceptance, which we don't have nowadays. But disadvantage, low statistics. At the beginning, people, scanners have to manually analyze these events. Later, it was automatized. And no or very poor particle identification. So that's the right plot is what Na61 records, argon-scandium collision, 150 GeV over C. We are talking now about fixed target experiments. In most of the cases, when you see energy, this is a laboratory energy of the projectile. 150 means that single nucleon has 150 GeV over C. A means that if I have a nucleus with 100 nucleons, then the total energy will be 150 times 100. What square root of S is per nucleon pair, this energy is about 17 square root of S. So it's somewhere in the best energy range. Now, properties of this data, high statistics, good PID, but limited acceptance. And now let's introduce notation I will use in the first part of my presentation. N charge, and CH, number of all charged particles produced in a given collision. We have first, when you study this N charge, you see that what you see immediately in your study in 4π in particular, you see immediately charge conservation. Right? Initial charge has to be equal final state charge. So if you talk about N charge can change only by 2. You have to produce plus and minus particles in order not to violate balance of charge. So it is useful to introduce, say, multiplicity variable, call it, N, capital N, which can change by 1. It's a integer, non-negative integer number, 0, 1, 2, 3, and so on. And then from electric charge conservation follows that if you take PP collision, initial charge is 2, right? Each proton is charge 1. So the N charge, which you see in the final state, is 2. This is initial charge, plus 2 times our multiplicity variable, because you have to, this 2 stands for producing at the same time plus and minus positively, negatively charged hadron. Right?
Don't you produce any neutral particles?
You see this experiment. Yes, of course but we are talking about the N charge here. So the CH, you of course produce neutral particles, which, however, in all these experiments, you either don't measure at all or measure it very poorly, like a decays of lambdas, right, with a low probability and so on. By zeros, you may measure on the extremely low efficiency when they decay into gammas. The gammas may have a low probability to be converted. Then from the conversion of two gammas, you can try to reconstruct a pi zero. But essentially, these experiments measure charged particles. This is because of experimental.
Multiplicity variable means only charged particle. It only counts charged particles.
Yes, exactly. Right. It means only charged particles. It's oriented towards experimental data. We will analyze here. Right. Then for E plus E minus collisions, I will mention them. Initial charge 0. Then you have 2 times n. If you will have antiproton collision, initial charge will be -2, and then plus 2 times n, and so on. Good. So that's very easy. Then the second slide on the notation, Pn, of course, will be probability distribution of our multiplicity variable. And then something new, which is not popular anymore. It was very popular when people started to study event by event fluctuation, high energy collisions 50 years ago, right? We are talking about the 70s. This is beginning of event study. And the basic variable was so-called dispersion of probability distribution. This can be second, third, fourth order, general kth order dispersion. And how is it defined? It's a kth order central moment, n minus mean n to the power k average, but square root of it, not square root of it, but to the power 1 over k in the case of variance, or the D2, say, second dispersion, it is just square root of the variance. Okay? So there's no magic, very easy. We were used to cumulants, to central moments. It is just a square root of the central, not square root for the second central moment will be, so the second dispersion square root. If higher moments, it will be to the power of 1 over order of the moment. Yeah, I started to talk about the scale variance from the very beginning. So the scale variance is denoted like a W here, omega, sorry. And this is just variance over mean, scale variance. And the second dispersion is square root of the variance. Square root of S, of course, it's square root of S. Reference multiplicity distributions. I will tell you now something again pretty trivial, but it's preparing us to go to the predictions of statistical models. First, I will start with a binomial distribution as an important reference distribution. So imagine a box of volume V0, and we independently, randomly create in this volume V0 N0 particles. We put their positions according to the uniform probability density function, uniform in space, 1 over V0. And then then you can ask yourself, what is the question we ask yourself, what is the probability to measure n particles in a subvolume of the V0, which we denote V, right? So we have a big box V0, N0, and subvolume V, and ask question, what is the probability distribution to find n particles there? And you all know that answer is trivial. It will be binomial distribution. Standard formula here, the Q is just a probability for a single particle to hit V. It's just V over V0. And what is important to note, of course, n has an upper limit. It's n0. I cannot find in V more than n0 particles. Moments mean multiplicity is Q times n0, variance Q times 1 minus q and 0, and then scale variance, our quantity, will be 1 minus q. And then you see, of course, if my v is equal v0, so I just count particles in the whole volume I have, then I have always n0 particles, nothing fluctuates, and scale variance is 0, because it's 1 minus 1 is 0. So this is the case if we study fluctuations of conserved quantities like net charge in 4 pi, then it makes little sense. We will have always the same number. For proton-proton collisions, it will be always 2 charges, say, if we study net charge. So that this measurement makes little sense, right? That's one limit, that if we go to the full acceptance with the conserved quantities. The second limit, maybe I still comment to this binomial distribution, but this binomial distribution would later in a few minutes lead us to the prediction of multiplicity fluctuation in canonical and microcanonical ensembles, a bit less trivial. Actually, we will impose conservation laws here, conservation laws that n0 is constant, doesn't change from event to event. But we will impose not explicitly on a quantity we study, like number of particles, but a different quantity, like we say energy has to be conserved, but we study multiplicity fluctuations. What happens there with multiplicity distribution? But we are already prepared to say that probably scale variance will be limited by conservation law. Now, Poisson distribution. The same box, the same subvolume, but we consider now the opposite limit, not with v goes to v0, but we say, we consider so-called thermodynamical limit of binomial distribution. We say v0 and n0 go to infinity. My box, this v0 box goes to, its volume goes to infinity. n0 also goes to infinity, but such that n0 over v0 is constant. But we keep the v constant as well. So what happens is that our binomial distribution approaches Poisson distribution. You also know it perfectly well. Scale variance is 1 so variance is equal mean, scale variance is 1. Higher order moments you can calculate. And this actually brings us very close to the predictions of the statistical models in grand canonical ensemble. And to the most naive prediction is just scale variance is equal 1. Note that for Poisson distribution, n is unlimited. I went with n0 to infinity. So in principle, n can be arbitrarily large, right? So I don't have a limit of n. Conservation laws are acting in average, just fixing this ratio in 0 v 0, but not explicitly on event by event level. So for each event, and for a given event, n can be arbitrarily large, like in statistical models in grand canonical ensemble. Now that's so far the introduction. Now goes to the basic experimental facts. 73. Wroblewski formulates so-called Wroblewski law. He looks at the first data from this bubble chamber experiments on PP collision. Actually, these plots are a more recent compilation, not very recent, but very still up-to-date compilation of the data, not the data Wroblewski in 73 considered. And what he found is that he plots the second dispersion as a function of mean multiplicity, and he finds it goes linearly up. He plots the third dispersion, goes linearly up. Fourth dispersion goes linearly up. Very good. Sometime later, people repeat these plots for E plus E minus collision and find the same. Up, up, up. So we have this linear increase of the dispersions of any moment with multiplicity. And now we confront this experimental findings of Wroblewski law, this experimental finding, regularity, with what we learned about Poisson distribution, or I already imposed that it's prediction of statistical models. So Wroblewski say, or data say, D2 is proportional to n. I square both sides. I have variance, but you remember that D2 was the square root of variance. So I square variance and then n squared. Scale variance, ratio of the two, is proportional to n. So Wroblewski law gives this proportionality of scale variance to n. This was one of the first plots I showed, right? With PP data present exactly in this representation. And then you go to the Poisson distribution. We just reminded ourselves Poisson variance is proportional to n. Means scaled variance is 1. I'm just repeating, right? So you see here scaled variance is proportional to n. Here is 1. So this is how this dramatic plot appears here, right? Scaled variance and Poisson, kind of reflecting statistical models, qualitatively at least, and the data on PP, E plus, E minus collisions. Now, Wroblewski law is equivalent to the Carnot scaling. So what is Carnot scaling? Koba, Nielsen, Olesen, I believe this was a physicist from Denmark, 72, was actually 1 year before Wroblewski, from the theoretical consideration postulated that the multiplicity distribution in PP collisions should obey such a scaling in such a kind of scaling quantities. So multiplicity with given event, I divide by mean multiplicity, scale by mean multiplicity to put different energies together, right? But then I multiply probability distribution by mean energy, just to preserve common normalization of multiplicity distributions. So we do this experiment, collect all data on PNs in different collision energies, and we see actually they sit on top of each other. There are no different curves here. Groups of points correspond to different energies. There is a single curve indicated by the data. You can do it on the logarithmic scale here. See that it also in the tail. It looks sort of pretty well. So to summarize this finding, Carnot scaling, multiplicity distributions plotted in the Carnot quantities, mean n, Pn versus n over mean n, are independent of collision energy. What does it mean? Different formulation in Pn for different collision energies can be described by a single square root of S energy independent function. This is the scaling that in principle, these PNs are energy independent, but if you plot them properly, this presentation is independent then on energy. So this function we can write like this. Of course, we are talking about mean n times Pn, right? If I say mean n times Pn, move this mean n to the left, and this is this kind of scaling function, and there is no energy here in the bracket. It depends only on the scaled multiplicity. So then Pn is nothing else but 1 over mean n and this energy independent scaling function Kn. Now, I said already that Kn scaling is approximately obeyed both by PP and E plus E minus interaction, but there is important but that the form of the scaling function is different for PP and E plus E minus collisions. And before showing you the form for both, I want to introduce you to so-called lognormal distribution. So because that is psi function, the scaling function approximately obeys is a form of lognormal distribution. So I'm writing then to introduce notation z is a n over mean n to simplify, and then the scaling function cz is some constant factor 1 over z plus c, and then you have something which resembles exponent of the Gaussian, but instead of z or n, we have here log z. So actually log z plus c is distributed normally. And then if you go to the shape of this log normal function, this x here should be replaced by z. In z, you have something very asymmetric, which is a property of multiplicity distribution E plus E minus and PP collisions. Now, does it make sense? Why we see in data log normal multiplicity distribution? So this is again kind of elementary introduction. Normal Gaussian distribution appears in additive processes where changes of the quantity x, these changes in each step, delta x changes, are independent of the value of x. So if we start from the value x0 at step 0, then x step 1, x1 is x0 plus delta x1. x2 is x1 plus delta x2. These deltas are generated from the same random variables, generated from the same probability distribution, and generated independently of each other. Then after the k steps, xk minus 1 plus delta xk, you combine everything, you get x0, starting value, plus sum of delta xi. And then you apply central limit theorem, which says that this quantity will be then, this is normally distributed around 0. You start from x0, so you have a normal distribution centered at x0. So this is how you got the normal distribution, assuming that we have additive processes. And now we move to multiplicative processes. Assume that delta x is proportional to the value of x. It's not independent, but it's proportional. And x1 is x0 plus epsilon 1. This will be this proportionality factor times x01. Right? I put x0 in front. I have x0 bracket 1 plus epsilon 1. And so on, and so on, and so on. xk, x0, product. Instead of plus sum, I have a now times product of 1 plus epsilon I. Okay, then I take, of course, if I have a product, I take the logarithm of xk over x0, and then I have sum of logarithms. And under each logarithm, I have a random variable, right? So again, I can apply central limit theorem and say this sum of what I have under the sum, on the new random variable, is normally distributed, central limit theorem, but that's not epsilon. The xk is normally distributed by the log of xk is normally distributed. And this brings us to this log normal distribution function. So non-logma distribution function is almost as special as normal distribution function, right? It appears if what we have in physics, in nature, is a multiplicative process. Not the additive process, but multiplicative one. Now, how we can connect this to physics we are talking about? Imagine, for instance, E plus, E minus collision. The string which is stretched between, so E plus, E minus, quark, anti-quark, string stretched between them, and the string decays into two strings, right? And then this two strings also will expand and decay into next, each one two strings and so on. So we have a branching process, and actually from a very simple model saying that you have initial energy square root of s, then you generate randomly what fraction of this energy goes into potential energy of two strings, product of decay of this string at a given step, and what goes to kinetic energy. And then you have the second random variable saying, okay, I have now energy, potential energy of both strings. I have to still generate what fraction of this total energy is taken by one string and what by second. I do it, and then you, from such a simple Monte Carlo, you will get a log normal distribution. So actually this log normal makes sense if you think about the physics of E plus E minus and probably PP interactions. Now, going back to the data, this scaling function psi, I already announced that it's very different for E plus E minus and PP. How it looks like, E plus E minus is much narrower. That's the fitted to the data shape. PP is much broader. That's the shape fitted to the data, right? I don't have to talk about which energy, because this is energy independent. Can we understand in all this? Well, yes, probably, right? We can imagine now that proton actually is much more complicated than E plus E minus collision. You have all the quark-gluon structure. You can have many strings, energy of this initial strings stretch between quark, quark, diquark, quark pairs, whatever you can imagine there may vary. Number of the strings can vary. But if this fractional variation, what energy goes there, how many strings initially you stretched, is collision energy independent. So it means that you have the scaling variance of this branching process. Then you naturally get that if you assume log-normal distribution in E plus E minus, you will get in such a superposition model also log-normal distribution in PP, but with a much broader scaling function which reflects all possible variations in number of strings, which in a moment we will say this will be how we will move from PP to AA, right? Instead of strings, we'll talk about the wounded nucleons and so on, participants. And of course, if you average over different number of wounded nucleons, you get a broader multiplicity distribution. So you can understand at least qualitatively why, first of all, in E plus E minus, you have log normal, and then why in PP this log normal may be preserved, assuming that again it's string branching process in PP, but then you have many maybe strings with varying energies and so on. But if you, again, I repeat, assume scale invariance, energy invariance of these random variables, we talk about the fractions or numbers of strings, fraction of energy, then the scaling is preserved. So this, we are now very well prepared to move from PP to AA collisions. Here the model which we typically use is so-called wounded nucleon model, right? Or its variation of the hygiene and so on. They largely good main properties of this model are reflected there. So we collide two nuclei, then some of them, the red ones, interact inelastically. We call them wounded nucleons, and then they decay. Instead of strings here, we call about nucleon decay, but you can think about the strings and you can stretch them maybe between different wounded nucleons as well. Important is these processes of decay are independent. Then the total multiplicity in such an event is sum over multiplicities coming from the single decay process, say wounded nucleon decay process. Yeah, that's just additive formula. Now you take wounded nucleon model and ask, then it's back of the envelope derivation, what is the mean multiplicity in the wounded nucleon model in AA collision, right? Capital N is now in AA collision, nucleus-nucleus. Its mean multiplicity in AA is equal mean multiplicity emitted by a single nucleon times mean number of wounded nucleons. That's very easy. Now, variance is a bit more complicated. So variance of multiplicity distribution in NA has two components. The first one is a variance of multiplicity distribution from the single wounded nucleon times mean number of wounded nucleons. And the second, usually we call it wanted term, wanted component. The second is the variance of number of wounded nucleons. And the scaling factor is mean multiplicity in the wounded nucleon square. Okay, that's no magic. It just follows from this additivity of the formula relation between lowercase n and capital N. Then you calculate scale variance, and you get scale variance from the single wounded nucleon times scale variance of number of wounded nucleons scaled by mean multiplicity from the single nucleon. And then what happens, of course, you see that scale variance is you can do the whole procedure for PP collision, and you get the following relation. So it will be scale variance in PP. Instead of wounded nucleon, I talk PP collision, and then it will be the second unwanted term, which increases with variation of number of wounded nucleons. So prediction for AA collision is that you have a lower limit, it's a PP line for the scale variance. And then, depending how large a variation in the number of wounded nucleons, you go above this lower limit by this or other amount, right? So this area is the wounded nucleon model allowed area. You have a lower limit, this PP line for nucleus-nucleus collisions. You can be above if the variation of number of wounded nucleons is large. And below, you have wounded nucleon excluded area. Now we confirm this prediction with the experimental data on nucleus-nucleus collisions. So what happens, we go to results from today. So as I say, today experiments are characterized by high statistics but limited acceptance. So instead of this beautiful Kerr's simple prediction, we have everything convoluted with the acceptance. So these are data from NA61, but any experiment had these now properties of limited acceptance. But qualitatively, we can learn a lot. So we have data on PP. It's a PP, square root of S, are the gray points here. Good. So they increase. I just was saying that this is 1, this is mean multiplicity, so negatively charged particles. So this crossing of the statistical model prediction and PP data, we see in our data, NA61 data, of course, much more suppressed by the limited acceptance, but we see it. You see the line crosses 1 here, the gray point crosses 1 somewhere in the middle of SPS energies. Beryllium. We've selected very, very central collisions, 1% only. Overlaps with PP. Perfect. This is what we wanted. Very central collisions. We have no fluctuations of wounded nucleons. PP, beryllium should be equal PP. And then we go to argon scandium, also very central collision. And then we go down below 1. See? Above 1. That's a future of this scale invariant branching, say, strings seen everywhere. And then below 1, we are narrower than Poisson. Now we have to come back to the statistical model in microcanonical formulation to really confront this in more detail with the experimental data on argon scandium. You already have seen that binomial distribution gets, of course, is below 1 scale variance in general. But we are talking about production, not here, this was fluctuation of not conserved charge. Then it stays as binomial distribution, forget the correlation momentum space. But we are talking about the negatively charged particles. And then charge conservation has no direct impact on multiplicity of negatively charged particles. So the famous paper of Mark and colleagues, microcanonical formulation, this is a Mickey Mouse model, but illustrates the problem here, gives a solution. So we have a box when we say energy is conserved. Energy is not number of particles, but energy, easier. We have ultra-relativistic gas, particles are massless, and they have charge 0. So the charge conservation doesn't work here, right? Particles number is not conserved. In this model, particle number can be infinite. The Boltzmannians, it can be infinite large because I can have infinitely large number of particles which move which don't move, don't have kinetic energy, and then the number goes to infinity. So if one performs calculation in this model, then one gets that for the large mean multiplicity distribution is more or less Gauss-like, but the scale variance is 1/4. It's just quarter of the scale variance for the Poisson distribution, right? And this seems to be what we qualitatively see in the data, that the scale variance went below not only below the wounded nucleon prediction, right? Because this will be going below this group of points for top energy. But we also went below 1. So there are two dramatic events. We went below the wounded nucleon allowed region. This is where the wounded nucleon. And the second dramatic event, we even went below 1, which is a prediction for grand canonical. So this is illustrated on this plot when we have scale variance at top SPS energies, the mean number of wounded nucleons, PP beryllium, that's wounded nucleon. Wounded nucleon allow, if we don't fix centrality properly, allow a beryllium point sitting somewhere here above. But then we go to argon scandium, and we are in the excluded region by wounded nucleon, below wounded nucleon line, and excluded region by statistical modeling grand canonical approximation. So we called this effect, this rapid change from PP beryllium regime, which we try to argue scale invariant branching describes these processes. We go to something which looks like a microcanonical ensemble fluctuations with this rapid switch onset of phi.
Hey, Marek, you have 15 minutes. So
I am looking with, I said the first part is half an hour, and I have,
okay,
yeah, plan only one part for the, but then I can stop any moment. So what we do, we discover this effect in our first part of NA61 data taking, which this was between 2009 and 18. You remember we recorded data on these green boxes, I recorded data, and then we discovered this effect with this data. But we don't have data between argon and beryllium. So we want to, after LS3, 26, 31, take data which will cover this region in detail of the onset of the confinement. It's our current plan to attack this discovery. Now, last 12 minutes, critical point search only by intermittency. So the confinement critical point, hypothetical endpoint of the phase transition line, QGP radiometer, that has properties of the second order. Introduced in 89 by two groups independently. Search for critical point at SPS. It is scan in collision energy and nuclear mass number. By this scan, we hope to move freeze-out point, and we want to move it close to the hypothetical. If there is a critical point, by scanning, we want to move to the critical point. If we are close to the critical point in this 2D scan, we expect a maximum signal of critical point, so-called hill of fluctuations. I already showed what we did for this scan. Okay? These are these green boxes. This is the data we recorded and slowly, tediously analyze them and release results one by one. Now, critical point and intermittency. So considerations, this is this golden period of critical point, 88, 91 probably. This is the several years which are really fantastic for the critical point instantly interacting matter. So critical point, we said, it's property of second order phase transition, scale invariance, power law correlation function, and then characteristic dependence of fluctuation of beam size scale at which you look at them. And then the tool to look for this, one of the tools, but we follow it, is so-called intermittency analysis. So what do we do here? This is an example which we now follow in A61 and A49 followed before. You have transverse momentum space, Px and Py. Pz is along the beam direction. We divide this two-dimensional space into square boxes. This is pixels here, so small delta. The total interval is capital delta. We divide by m integer under m, so we have a size of this small box here being lowercase delta, and in each of these guys we count number of r particles, say 2 pairs, maybe it's easier as that, first number of pairs of particles in each of these guys. Then I calculate average over all beams by summing over all beams and dividing by number of beams here, and average over all events. That's very easy, right? Number of pairs. Actually, you can do it for number of triplets. Then you will have scale factorial moments of the third order, and so on and so on. And you have to scale it, because this is why it's scale factorial moment. I just divide by mean multiplicity in beams of size delta. Right? So I calculate mean multiplicity, averaging over beams, averaging over events, and divide by this mean multiplicity to the power given by the order of factorial moment. So that's easy. Then Białas-Chwa was the pioneering paper on this, showed that if the single particle multiplicity distribution is uniform, which of course you say in PT, the Px, Py, of course it's not, but assuming it is, the scale factorial moment of order R as a function of number of beams, you divided the whole space, it has a power law dependence. Number of beams, pixels to the power of phi r, which is the r is because this r the phi depends on the order. And they say, if in addition, this is a really critical, serious critical point, not other power law dependence like from the scale invariant branching, then this phi r's powers should obey so-called a relation which, so if you divide this phi r, maybe like this, powers over r minus 1, then the so-called anomalous fractal dimensions, dr, this is called like this, should be independent of r. So if I do analysis for second, third, fourth factorial moment, I can, if I find the power law dependence, I can extract this power for each order and then check this relation's additional test. Everything was if single particle distribution is uniform. 30 years ago, Andrzej Białas introduced a primitive transformation to make it uniform. Of course, it is not. That's an example of Px, Py distribution from an A61 used for the intermittency analysis. But then you have so-called cumulative transformation, trivial popular, and you make it uniform. So this is the same distribution after transforming by this cumulative transformation. So this is the same distribution instead of Py, Px, it's Qy, Qx after transformation. This transformation goes through the probability density function of Px, Py. But I will not spend a longer time on this. So we make this trick in the analysis, we transform to uniform distribution. Now, so the summarizing what we expect if we are really lucky and we are close to the critical point, which gives us signal in what we look at in the intermittency of pions or protons. We expect a power law dependence of factorial moments of any order. Then the anomalous fractal dimensions extracting from these powers should be independent of order. Very good. And then, of course, I started from this. The signals should be observed only in a given limited region of collision energy and a nuclear mass number. There are many, many properties which I don't want to discuss because of the limited time. other properties which are nice here. We have two Mickey Mouse models to quantify sensitivity of our data to potential critical point when one assumes a power law correlation function, again, without going into details. These are the parameters of the model. Parameters of the model is, of course, this power. For instance, for 2 factorial moment for protons, QCD-based considerations say power should be of the order 0.8. That's the example for 0.8. And this is the fraction of protons to all protons which are critical. So they are really generated from this power law correlation function. Others are generated from the single particle distribution correlated. So we are in the region of the percent or per mil, right, scanning here. This is why, because it appears that our data are extremely sensitive. So if you, in the moment I will show you that the curve for 1% here, contamination of critical protons, is completely excluded by the data. Yeah, these are the data. So it's an example of protons in argon-scandium collisions at 150 GeV, 2nd factorial moment, number of pixels in px, py space. You see nothing, flat. Phi is 0, or fraction of protons, critical protons is 0. Different centralities, all centrality combined, statistically, of course, much smaller, nothing. And now I just sketched here this line, 1% of protons correlated with phi equal 0.8. It's like this, right? So you see the data, wow. So we are now working on the constructing exclusion plot in this for the Mickey Mouse model, 2 parameters. And then we can have a region which is excluded by the data, which will be very low phi 2s, I don't know, 0.2, 0.3, and very low numbers of critical protons are allowed by this high precision data. But the conclusion is for a moment set, no signal observed yet. But we look only at a very small fraction of the data we recorded. There are these underlined boxes here, read what we already released as a preliminary of published, and these guys are just under analysis. So there's a lot of work still to continue. Actually, surprisingly, I managed. So the second part was faster. I am at my summary. So I was talking about the multiplicity fluctuation, tried to convince you that multiplicity fluctuation, multiplicity distribution, right? I was talking mostly about distribution, actually, itself. In E plus E minus, proton, proton, and probably beryllium, beryllium, one can understand as a superposition of processes in which you have scale invariant branching, which leads to the lognormal distribution. You can then, of course, overlap them, combine, superimpose. You get a broader lognormal distribution or narrower after this process. However, argon-scandium and lead, I didn't touch this, but actually the first observation of suppression of scale variance below 1 for negatively charged particles was for central lead and E49. One of my PhD students in Frankfurt here many years ago discovered this, published. We just confirmed this in argon-scandium. And that's perfectly described very perfectly. It's easy to understand in statistical models you need to impose conservation laws, at least canonical ensemble, probably microcanonical. We have a paper when we compare with quantitatively with both, with lead data, and then MC fits better. And then because of the limited acceptance, you have quite uncertainties in comparing model with the data. So the conclusion, what is it, is probably open, but qualitative conclusion, I think, is pretty solid. Critical point search, no signal observed yet, but still many reactions to be analyzed. Okay, I